Sorry, I just turned on the recording. Sorry, it's about 5 minutes after we started. So please type your name in now. If you typed it in before the recording, then I don't have a record. Sorry about forgetting to turn on the recording. Okay, so the sequence of partial sums has no limit, and if you tried to just use the formula in this example, you'd get a two in the new. Sorry, you'd get a one in the numerator, and then you'd get r equals two. So you'd have one over one minus two, which is equal to one over minus one, which is minus one. So you'd get that the sum of this series is equal to minus one, which doesn't make any sense, right? So you can't use this formula unless the common ratio is between minus one and one. That's the only way that it works. Okay. All right. So this formula. The good thing is this formula is very easy, right? So are there any questions about how we use this formula? Sure. Okay. So with this, let's just go over the homework problems, which
Robert?
won't take very long. Abraham, yeah.
Yeah. So if the sequence or series is in this form, what would be
Mhm.
the formula, the best formula to use to find the sum of the series?
Right. This is it. This formula right here. So the sum of
Yeah.
the series is exactly here. A over one minus R.
Yeah, what I'm saying,
Hmm.
hello,
Yes,
if the
Abraham.
common region is greater than one,
Oh, okay. Then the
which formula can
series
we?
has no sum. You just say it diverges. You can't say what the sum is,
Oh, okay.
or you say it's
So that is
infinity.
the
Right. This
infinity.
this is this example. This series has no sum because it doesn't converge. The numbers just keep getting bigger and bigger. There's not going to be a finite sum, right? It just goes up to infinity, right?
Okay. Thank
Whereas
you.
something like this one is going to converge. The numbers are getting bigger, but they're getting bigger very slowly. And when you add them all up, it still only gets you up to one, right? That's the difference between a series like this, where the ratio is one half, versus a series like this, where the ratio is two. Okay,
Yeah. Thank you.
you're welcome. Other questions? Okay, so let's now just
Robert?
go. Wait, question? Yes? James? James? Caselli?
Yeah, so the endpoint of the yeah, you get me? Yeah, the
Uh,
numbers.
okay, not perfect, but good enough.
I'm saying because we know that when we keep adding up the geometric sequence, it will get to a number that is the implant endpoint or number that we are reaching to because it's less than one.
Right. Yeah, so when you add it up, it's the limit, right? So as long as the ratio is less than one, it ends up converging to some finite number. And at every step of the series, you get closer and closer to that number, and that number is the limit when you take all the terms.
All right,
Okay.
thank you.
Yeah, you're welcome. Okay. Other questions? Okay, so let's do the first homework. This is a geometric series, and this is just a straightforward application of the formula. Right, so evaluate the sum of the following geometric series. We know that the formula is just going to be a over 1 minus r, right? So in this series, what's a for this series and what's r for this series?
So looking at the things, the A will be the first thing,
Yeah, great, Princeton. So what is that?
which is 18.
Great. So a in this case is 18. It's just the first term. And what about r? We need to know what is each term getting multiplied by to get to the next term.
Yeah.
Yep.
Robert?
Abraham, yep.
So yeah, what we
Let's
do
say
now
that
is
R will be equal to 2 or 3.
Exactly, right? So the ratio is 2 over 3. This is the common ratio. And the way you can find it is you just take any two terms and take their ratio. So for example, you can just take the first two terms, right? R is going to be 12 over 18. And if you want to find the common ratio, you can always just take it as the second term divided by the first term, right? Okay, and then this simplifies to 2 over 3. Okay, but it doesn't have to be the second term divided by the first term. You could take the third term divided by the second term, or you could take the fifth term divided by the fourth term. You just take any term and divide it by the one before, and that's what gives you the common ratio, right? That's how you can find common ratio. Okay, good. So now you just punch these into the formula. So the sum is equal to 18 divided by 1 minus 2/3. Perfect. And that's 18. 1 minus 2/3 is 1/3, right? Which is 18 times 3 over 1. And that comes out to be 54. Okay, so the sum of all of these terms is 54. And maybe just as what I'll call a sanity check, just to make sure this is a reasonable answer, let's write out some partial sums, right? S1 is going to be 18. S2 is 18 plus 12, that's 30. S3 is 18 plus 12 plus 8, that's 38. S4 is 18 plus 12 plus 8 plus 16/3, and that's equal to, well, 16/3 is 5 1/3, so this is 43 1/3. Maybe I'll write out one more. S5 equals 18 plus 12 plus 8 plus 16/3 plus 32 ninths. So 32 ninths is 3 5 ninths. And so you add 3 ninths. So this, I'll just do this in my head. This turns out to be 46 8 ninths. And so on. And the point is that it seems reasonable that the partial sums are approaching 54, right? I mean, 18, 30, 38, 43 1/3, 46 8 ninths. Each one is going to add a little bit more. They're getting to 54, but they're also increasing slower and slower. So you can imagine they're going to slow down until they get to 54. Right? So this is just a check. This isn't going to give us the answer, but it's checking that this answer isn't ridiculous, right? It seems like 54 totally could be the limit of this sequence if you throw in some more entries. Okay. Okay, questions on this?
Russ?
Yes. James?
So, is how many sum you're finding for tremendous? How many sum you're finding for a tremendous series? Because if for is let's say calculating maybe the first, second, third, it continues to another number. Before we're gonna stop to.
Sorry, you're not coming through so clear. I'm getting you. Yeah.
I'm saying like the answer we got 54. So if we have to add another term to the geometric series, are we going to get a value more than 54?
No, we'll never get more than 54. So if we keep doing more terms here, they're going to get bigger and bigger, and they're going to get closer and closer to 54. It will never actually reach 54. Because to reach 54, you need all of the terms. So it's never going to actually reach 54. It's just going to get very, very, very close at any finite stage. And then in the limit is 54.
All right, thank you.
Okay, you're welcome. Yeah, so it will never get higher than 54.
What was that?
Yes, other question?
Rash,
yes.
No, that question, Jenkins, my phone is almost to go off. Jenkins when you go off.
Okay.
Phone battery is very low.
All right, sorry about that. Thank you for letting me know. Yes, we can say the series converges. So we say, yeah, if we want to write this in words, we say the series, this is Armstrong's question, series converges to 54. Yeah. Other questions? Okay, let's move to the next problem. So next problem says, does the following series diverge or converge? Justify. So 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. Okay. So there's a cheating way. The cheating way is to realize this is actually a geometric series with common ratio minus 1, because each term is minus 1 times the previous one. But let's not do that. Let's just do this directly from the definitions. Okay? So what do we need to do to know if the series converges or diverges? We've got to just write down the partial sums. That's the definition of convergence or divergence, is you have to do the partial sums. So what's our partial sum? So A1 is 1, first term. A2 is 1 minus 1, that's 0. Oh, sorry, not A2. Sorry, this should be S1, S2. S1 is 1, S2 is 1 minus 1, that's 0. S3 is 1 minus 1 plus 1, that's 1. S4 is 1 minus 1 plus 1 minus 1, that's 0. S5 is 1 minus 1 plus 1 minus 1 plus 1 equals 1, and so on. So you can see the pattern, right? The pattern is that the sequence of partial sums is 1, 0, 1, 0, 1, 0, 1, 0, 1, etc. So does this sequence converge? If we have 1, 0, 1, 0, 1, 0, 1, etc., does this sequence converge? Does it have a limit? Does the sequence have a limit? Yes. What's the limit? One. Okay, so it's a reasonable answer. So the limit could be one. There's a lot of ones here, but at the same time, there's a lot of zeros. So maybe the limit is 0, right? We got 1 and 0, right? So one thing is that a sequence can only have one limit. Okay? And if you go back to the definition of limit, right? Definition of limit says that if 1 is going to be the limit, that means that you have to be able to get arbitrarily close to 1 by just going far enough out in the sequence. So it's a little tricky here, but you can't actually do that because no matter how far out you go in the sequence, there's still going to be a bunch of zeros. So there's still going to be a bunch of entries that are far away from 1. Okay, so the actual answer is that this sequence has no limit because it oscillates. Okay, so this sequence has no limit because it oscillates. You can't tell whether the limit's going to be 1 or 0. It can't have two limits. Okay, it just bounces between 1 and 0 and 1. It's not approaching any one number. It's bouncing back and forth between two numbers. That means no limit. Okay, so this sequence has no limit because it oscillates. And that means that the series has no limit. So it diverges. Okay, maybe I shouldn't even say the series has no limit. We didn't talk about the limit of a series. I should just say that means that the series diverges. Right? Think about it this way also, like, right, what could the limit of this series be? I could put parentheses around all of these and it would look like 0 plus 0 plus 0, etc. That would give me 0. Or if I wanted to do it differently, I could put I could put parentheses around here, etc. And then I'd get 1 plus 0 plus 0 plus 0, etc. And that would equal to 1. So is the sum 0 or 1? And the answer is you can't tell. You don't know whether it's going to be 0 or 1. Just like with these partial sums over here, you don't know whether it's going to be 0 or 1. And when you can't tell, series just has to diverge. If you're going to say the sum of the series is something, you have to know what it is. There can't be two answers. Okay, so this series diverges. Okay, even though the numbers don't get big, the series still diverges because the sequence of partial sums does not have a limit. Okay, there is some way of saying that the sum of the series is 1/2. That's a kind of weird answer. There is some aspect in which that answer can be justified, but not using the standard definition of the sum of a series. Okay, so really for this series, we say any kind of sum we could give it is going to cause problems. So we just throw up our hands and we say, we can't sum this series. It diverges. Too bad. Okay, so this is divergent series. You can't sum it up. Okay, questions? Okay, let's move on. This is homework exercise 3. This one's a little confusing, but James wrote up a good solution to this that maybe he'll send out to the main chat because it was very nice. So we'll consider the interval 0 to 1. We remove the middle 1/3, then we remove the middle 1/3 of each of the 2 segments that remain, and now we remove the middle 1/3 of each of the 4 segments that remain and keep doing that out. So the points that remain are called the Cantor set, and how much total length has been removed and what is the total length of the Cantor set. So if you remember last time I drew this diagram, here we have 0 to 1. Then at the next stage, we're removing everything between 1/3 and 2/3. So we have 0, 1/3, 2/3, 1. Then at the next stage, we're removing the middle thirds of each of these intervals. So this becomes 0, 1/9, 2/9, 1/3. 2/3, 7/9, 8/9, and 1, and so on. I mean, I guess the next one I won't really write the numbers because it's too hard, but I'll just draw what's going on. We basically remove the middle 1/3 of each interval. Okay. Oh, sorry, James. Okay. Well, the participating through chat is good. We still get what you say. Okay, and so on. So this is the Cantor set. So when you keep doing this out to infinity, you get the Cantor set. The Cantor set is an example of what's called a fractal. Okay, so it's maybe one of the easiest examples to write down of what's called a fractal. Something that when you zoom in, it looks the same as what it looks like when you zoom out. Okay. So let's look. What do we have for the amount removed? Let's look at the amount removed at each step. So the amount removed, the question asks how much total length has been removed. So let's see how much is the length that's removed at each step. Okay, so let's see the length removed at each step. Well, for the first step, we remove 1/3, right? For the next step, what's getting removed? We're removing 1/3 of this and 1/3 of that. So that's 1/3 of 1/3, so that's 1/9. And here we have 1/3 of 1/3, that's 1/9. So we get 1/3 times 1/3 plus 1/3 times 1/3. That's going to be equal to 2/9. Now how much gets removed here? Well, we have 4 intervals, and each interval we're removing 1/3 of the interval. So each interval has length 1/9, and we're removing 1/3 of it. So we're going to remove 1/27th from each part. So here we have, 4 times 1/27th, and that's going to be equal to 4 over 27. And then if we were to continue it, we now have 8 different pieces here. And each piece has length 1 over 27, so we're going to remove a third of that, which would be 1 over 81. So at the next step, we would have 8 times, I'll do times here, times 1 over 81, right? Which would be 8 over 81, and so on. So this is how much we're removing at each step. And if you look at the pattern, what you see is that at each step, the number of intervals doubles, and the length of the interval gets divided by 3. So at each step, the amount that you're removing is 2/3 times the previous step. So it's asking how much total length has been removed. So total length removed is what? It's 1/3 plus 2/9 plus 4 over 27 plus 8 over 81, and so on, because you're going out to infinity. Right? Going out to infinity. Okay? And now what do you want to notice here? Well, this is a geometric series. Sorry, my writing is small. I want to get it on this page. This is a geometric series with a equals 1/3. That's the first number. And r, well, what do we have here? Each number is 2/3 times the previous number. You get the 2 because you're doubling the number of intervals, and you get the 3 because each interval is 1/3 the length of the previous interval. So 1/3, to get the next term, you multiply by 2/3, then you multiply by 2/3 again to get 4/27ths, then you multiply by 2/3 again to get 8/81ths, and so on. So our r here is equal to 2/3. Okay? So what you get, so the total length removed is going to be a over 1 minus r. That's our geometric series formula, which is 1/3 over 1 minus 2/3. And that's equal to 1/3 over 1/3, and that's equal to 1. Okay? So if you repeat this out to infinity, then the amount of length that you remove, the total is 1. And that means the total length of the Cantor set, which is what's left, well, you started with something of length 1, and you removed something of length 1, which means what's left has to have length 0. So what's left has length 0. Okay, so the Cantor set has length 0. And so you remove length 1, what's left is length 0. That doesn't mean you've removed the whole thing. What means is that what's left of the Cantor set is a bunch of isolated points. And all of those points have length 0, and when you take them all together, it still has length 0. There's no actual intervals left in the Cantor set. Everything is just isolated points, so the total length is just going to be 0. Okay, this is actually, like, if you're a little confused by that, that's reasonable, because how do you define the length of some weird fractal like the Cantor set? It turns out that to set up the definitions requires a little bit of work to do it right, and we don't have time to do that now. But at least from this logic, it makes sense that we're removing intervals that sum up to length 1, which means that what's left should have length 0. And the geometric picture is after you keep removing all of these middles, you're left with just a bunch of dots, a bunch of, isolated points. And so even when you add them all together, the total length is still 0. Okay, so this is maybe the most basic example of what's called a fractal, this Cantor set. And fractals are used, all the time for computer graphics, for understanding coastlines, for understanding snowflakes, all sorts of various applications. This is maybe Cantor set itself is not used so much, but it's good for getting the first basic understanding of what a fractal can be. All right, any questions? Okay, so let's move on. So let's remember what I talked about at the end of last time. I gave you these mysterious series identities. Told you that 1 minus a third plus a fifth minus a seventh plus a ninth and so on is equal to pi over 4. That 1 minus a half plus a third minus a fourth plus so on is equal to the natural log of 2, like the power that you have to raise e2 to get 2. That seems crazy, right? And then 1 plus a fourth plus a ninth plus a 16th is equal to pi squared over 6. How would you ever figure any of this out? Okay, and well, we're not really going to be able to talk about how you figured this out, the last one. But the first two we're going to talk about today, and that's going to be the last topic. Okay, so we're going to deduce these using what are called MacLaurin series, which we're going to discuss today. Okay, so we have to talk about what's a MacLaurin series going to be. But first we have to build up a little bit of background. Okay. Oh, and so by the way, the stuff that we're going to talk about in terms of the book, let me just give you a chapter. Everything that we do today is in chapters 8.5, 8.6, and 8.7 of the book. But we're certainly not covering all of these chapters. I'm just giving you a very quick overview of what's going on. I'm not giving you every detail of how things are derived. Okay. Okay, so first I need to tell you what a power series is. To know what a MacLaurin series is, I need to tell you what a power series is. So a power series is a series where you take a sum, but not just of a bunch of numbers, but you add a variable x, right? This is going to be a variable, which we call x. And so if we take a sum of the form a n x to the n, or another way of writing this is we actually start from n equals 0. So we have a0 x to the 0, which is just a0, because x to the 0 is 1. So I can write this as a0 plus a1x plus a2x squared plus a3x cubed, and so on. That's what this sum means. And if we have this, it's called a power series. And you want to think of a power series as a function. Now remember, what's a function? A function is something that takes an input and gives you an output. So we want to think of a power series that takes an input for x, just like any function of x. You punch in something for x, and then if you punch in a number for x, you end up with a series. And if that series has a sum, that's the output. So we should think of it as a function that takes an input x and then returns the sum of the series that you get when plugging in x. Okay, and now maybe some x's aren't going to work. Maybe some values of x, if you plug them in, you get a series that diverges, that has no sum. Okay, that means those x's are not in the domain. You're not allowed to plug in those x's. But maybe for some x's it does work, and then that's okay. Those x's are in the domain of the function. So one way of thinking about this is that it's basically like an infinite polynomial, right? It's a polynomial. If we stopped it at the x cubed term, then this would be a cubic polynomial. It would be a degree 3 polynomial. But with a power series, you don't stop at any term, but you just keep going on forever. Okay, so a power series is like a polynomial, but it goes on forever instead of stopping at a certain degree. But it works the same way a polynomial works. You can plug in an x and try to evaluate it. The only issue is that with a polynomial, when you plug in x, you're evaluating a finite sum, and you can always do that. But with a power series, if you plug in x, then you're evaluating an infinite sum, a series, which maybe sometimes you can do, and maybe sometimes you can't. Okay, so this power series we're going to think of as an infinite polynomial. And I think it'll become more clear when we do an example. So maybe I'll hold off on questions until the next example. So let's look at this example. Let's consider this series where all of the a's are just 1. So all of the coefficients are 1. So I'm just going to take 1 plus x squared plus x cubed, so on, right? Okay, so over here, remember, I can take these coefficients to be whatever I want. If I take them all to be 1, then This is just the series I'm going to call. I'm going to say 1 plus x squared plus x cubed, or if you want to write it succinctly, you can write it like this: sum from n equals 0 to infinity of x to the n. Okay. Well, what is this as a function? So as a function, let's say if we plug in, let's say x equals 1/4, what do we get? We get 1 plus 1/4 plus 1/4 squared is 1/16 plus 1/4 cubed is 1/64, and so on. And this is a geometric series with a equals 1 and r equals 1/4, right? Each entry is 1/4 plus 1/4 times the previous entry. So the sum of this series is a over 1 minus r. That's 1 divided by 1 minus 1/4, which is equal to 1 divided by 3/4, which is equal to 4/3. Right? So if we plug in x equals 1/4 to this series, if that's our input, we get 4/3 as our output. So I can do maybe even like a table of values, right? If I do x, which is the input, then the output, well, if I do 1/4, I'm going to get 4/3 as my output. Let's do one more example. If I take x equals maybe 1/2, you get 1 plus 1/2 plus 1/4 plus 1/8, and so on. This is again a geometric series with a equals 1, r equals 1/2. And so the sum is going to be 1 over 1 minus 1/2, and this simplifies to 2. So if my input is 1/2, my output is 2. If instead I try to punch in something like x equals -1, well, I get 1, well, plus x, that's -1, plus 1, -1, plus 1, etc. And we already know that this diverges, right? We already know this diverges from the homework. So if I plug in 1, output, we get undefined, right? It diverges. And so on. You can do a whole bunch of other values. But in general, for any x, this is a geometric series with, well, a equals 1. 1's always the first term no matter what x is. And your common ratio here is what? It's just going to be x, because each term is x times the previous one, right? We keep multiplying by x to get the next term. So r equals x. So the sum is just going to be 1 over 1 minus x as long as absolute value of x is less than 1. Remember, we need to have absolute value of x to be less than 1 in order for the geometric series formula to work. So in fact, what we see is that this power series is just a fancy way of writing the rational function 1 over 1 minus x. Okay? And if you do this with 1/4, you'll see that it works. 1 over 1 minus 1/4 is 4/3. 1 over 1 minus 1/2 is 2. 1 over 1 minus 1 is undefined, right? But what it is this is just the function 1 over 1 minus x, but it's this function with a restricted domain. So the power series only gives the function 1 over 1 minus x when the absolute value of x is less than 1. Okay, if the absolute value of x is greater than or equal to 1, then power series is undefined. Those things are not in the domain. So in this case, the domain is just the set from -1 to 1. Okay. Anything else makes the series diverge. Okay, so this is a nice series because no matter what x you punch in, it's a geometric series. You can actually just think of it as a geometric series where the common ratio is the variable x. And so the sum that you're going to get from the geometric series formula is 1 over 1 minus x. All right. Any questions about this? It's a particular power series that if you plug in the right x's, you can get numbers. And if you plug in the wrong x's, you get nothing. You get diversion. Just want to remember what's on the next page. Okay, yeah, it's on the next page. So what we're going to say is that this function is actually just equal to 1 over 1 minus x, as long as you have the correct domain. Okay. All right, let's try another general thing. Okay, so now we're ready to talk about what's a MacLaurin series. So let's say that f of x is a function that is infinitely differentiable at x equals 0. That just means that you can take as many derivatives as you want, okay? You can take a first derivative, a second derivative, and so on, right? So we're back to calculus now. So what I want to do is I want to find, so here you're just given like a standard function, like f of x equals sine of x or e to the x or a polynomial, something like that. What I want to do is try to find a power series g of x where g and f behave the same way, at least at x equals 0. So where g of 0 is equal to f of 0, g prime of 0 is f prime of 0, g double prime of 0 is equal to f double prime of 0, etc. And so remember, what does g of x look like? G of x looks like a0 plus a1x plus a2x squared plus a3x cubed. Maybe I'll do one more term, a fourth x to the fourth, and so on. Okay, so in particular, g of 0 is pretty easy to calculate because g of 0, you just plug in 0 for x. Everything here just goes to 0, and what you're left with is just the one term that doesn't disappear. So g of 0 is just a0 here. So if you have a power series and you plug in 0, you always just get the first term. Okay, so I'm not going to worry about f for now. I just want to calculate some derivatives of g to start with. So let me take the derivative. Well, that's going to be a little bit hard. So I want to first get the general framework before we do an example. Okay, so that's not good because actually f of x equals x to the 1/2 is not infinitely differentiable at x equals 0. So once you take one derivative, you get 1/2 times x to the minus 1/2, and that's actually not differentiable at x equals 0 at all. So MacLaurin series don't apply to this. The Taylor series at a different value can. Okay, so what's g prime of x? Well, let me take the derivative. How do you take the derivative of a series? You just do it term by term, right? So the a0 disappears because it's a constant. The a1x just becomes a1. The a2x squared becomes 2a2x. a3x cubed becomes 3a3x squared. And then 4a4x cubed, and so on. And if I take g prime of 0, I plug in 0 for x, everything here disappears, and I'm just left with a1. I'm going to do two more. So what happens if I take another derivative? Well, if I take another derivative, that's just taking a derivative here. The a1 disappears. 2a2x becomes 2a2. 3a3x squared, I'm going to write this as 2 times 3 times a3x when I take a derivative. And then derivative of 4a4x cubed, I bring down the 3. So that's 3 times 4 times a4 times x squared. And again, if I punch in 0, I get g double prime of 0. Sorry, plus dot dot dot. I get g double prime of 0. Anytime I plug in 0 for x, those terms disappear, and I'm left with 2a2. Let me do one more. What happens if I do g triple prime of x? Well, I take another derivative. This is going to disappear. 2 times 3 times a3 is just going to give me 2 times 3 times a3 because the x goes to 1. And now the x squared, I'm going to bring down a 2. So that's plus 2 times 3 times 4 times a4 times x, and then more terms. And that means that g triple prime of 0 is going to be 2 times 3 times a3, right? I'm going to do one more actually. So g quadruple prime of x, so 4 derivatives, one more derivative, this disappears, and this over here, the x goes to 1. So I get 2 times 3 times 4 times a4, and then whatever extra terms. But if I punch in 0, these extra terms are going to have more x's. So g quadruple prime of 0 is 2 times 3 times 4 times a4. Good, yes. So what James has written is exactly correct, although we're not ready for this answer yet. Okay? There's no way we could derive this answer without a little more work. Okay? So I mean this is the correct answer, but we're not ready for it yet. So in general, the pattern shows that what happens if we take n derivatives of g at 0? Remember, this notation here means the nth derivative. The nth derivative at 0. Well, this is equal to what? Well, we saw the third derivative is we multiply up to 3, a3. Then the fourth derivative is we multiply up to 4, a4. The fifth derivative is multiply up to 5, and that's going to give us a5. And so what's that actually going to be? In this case, at step n, you're going to end up getting n factorial times an. Right? The nth derivative at 0 is n factorial times an. Right? Remember what n factorial means. This means 1 times 2 times 3, dot, 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 all the way up to n. And the 1 doesn't matter. I'm just throwing in the 1 here. You could put in a 1 here anywhere you want. Okay? So the nth derivative at 0 is always going to be, for any power series, is always going to be n factorial times an. So now let's go back to the original question. So what's the question? Somebody gives you f of x, and you want a power series where the derivatives of the power series at 0 all match the derivatives of f at 0. Right? So we want that the nth derivative of g at 0 should be equal to the nth derivative of f at 0. Well, we have a formula for the nth derivative of g at 0. It's n factorial times an. So if we want to solve for the an, this gives us that n factorial times an is equal to the nth derivative of f at 0, which tells you that your an is going to be the nth derivative of f at 0 divided by n factorial. So this is exactly the formula that James posted in the Zoom chat, right? So this is kind of the answer to the question. If you want a power series whose derivatives match the derivatives of f, at least at 0, then well, how do you make a power series? You have to choose the coefficients. And the way you choose the coefficients is by this, somewhat complicated formula. The coefficient of x to the n should be take n derivatives of f at 0 and then divide by n factorial.
Yeah, hello, sir.
Yes, Prince.
Yeah, thank you so much for this practice. Thank you so much for this work. But I have a concern with the formula which is just giving n which is equal to f derivative of n and multiplied by 0.
No,
So
it's not
if
multiplied by 0. It's not.
yeah.
This is not multiplied by 0. This means you take the nth derivative of f and then you punch in 0.
Oh, okay.
Right. Yeah, it's not
Because
multiplication.
I'll have a concern on it
Maybe
now because
what I'm going to do to make it a little easier is I'm going to draw it like this. That f to the n is that just means the nth derivative. That's a function, and now you plug in 0.
Okay, because I have a concern on it. I thought I'd multiply by
No,
0.
then it would just be 0 all the time. Right. No, of course you don't want that.
Okay, thank you.
Yeah.
I understand.
Yeah. Okay. So yeah. So you wanna do it this way. Okay. So this solves the question. I know it went a little fast. Normally we would take more time, but we're finishing up. But just recall, somebody gives you a function. You want a power series. If you choose the an using this formula, then your power series will have the same derivatives as the function, at least at 0. They'll have the same value at 0, the same first derivative, same second derivative, same third derivative, and so on. So this is a way to build a power series that shares a lot of the properties of f. Okay, so this is what we see. So from the previous slide, if we take this series where we give the an by this formula that we wrote on the previous page, then all of the derivatives of f of x at x0 are the same as the corresponding derivatives of the power series. And we give it a name. This is called the MacLaurin series for f. Okay? So all these MacLaurin series, what they are is, think, MacLaurin series. So MacLaurin series for f means a power series, all of whose derivatives match those of f at least at x equals 0. Okay, so it's like f is just some function. Can you build a series? I'm not claiming that the series is equal to f. I'm just claiming that the series has this property in common with f. It has a bunch of derivatives at 0 that are the same as the derivatives of f. So the series is kind of like the function f. And now what's really amazing, and this is called Taylor's theorem, and we're not going to be able to prove it, is that for most standard functions, the MacLaurin series for f actually does equal f, at least where it converges. This is a result that you can call Taylor's theorem. Okay. So the most amazing thing is that if you give me a function f, and if I construct a power series using this recipe, then usually the power series that I construct is actually the same function as f, maybe with a smaller domain. But basically, it's going to give you the same function. So this is the miracle. We're not going to be able to prove this, but it should be at least plausible, right? You have a power series where it shares a lot of information together with f. It has all of these derivatives are the same. Okay? So let's do an example. So let's consider e to the x. Let's say that f of x is e to the x. Okay, and I remember we're seeking the MacLaurin series, sum from n equals 0 to infinity of an x to the n, and the formula is that an is equal to the nth derivative of f at 0 divided by n factorial. This is the formula that we had. So let's just do coefficients. So a0 is going to be the 0th derivative of f at 0 divided by 0 factorial. Now for this you need some conventions. So the 0th derivative of f just means f. Just means don't take any derivatives. 0 factorial by convention is always equal to 1. So 0 factorial equals 1. This is a general convention in all of mathematics. 0 factorial is not 0, it's 1. Okay, so this is f of 0 over 1, which
Yeah.
just means
Yes,
it's
sir.
e to the 0 over 1, which is 1 over 1, which is 1. Question from Prince?
Yeah, so since 0 factorial is equal to 1, and 1 factorial is still be as a C number, is sir?
Yeah, 1 factorial is also 1.
Okay.
Yeah, 1 factorial is also equal to 1. Yeah. But that's maybe a little easier to understand. The 0 factorial equals 1 is maybe a little mysterious. 1 factorial equals 1 is what you would guess, right? It's just you take 1. Okay, so a0 is going to be 1. Let's calculate some more coefficients. So let's do a1. That's the first derivative of f at 0 over 1 factorial. Just means f prime of 0 over 1 factorial. Well, the derivative of e to the x, remember, e to the x had this great property that the derivative of e to the x is e to the x. So it doesn't matter whether you're taking a derivative. Yes, so I'm just going to recall also that d dx of e to the x is equal to e to the x. Right? So taking a derivative doesn't change the function. So f prime of 0 over 1, that's just, well, f prime it's just the same as e to the x, right? So this is just, again, e to the 0 over 1 factorial, which is 1 over 1, and it's again 1. I'm going to calculate two more. So a2 is the second derivative of f at 0 over 2 factorial. That's saying f double prime of 0 divided by 2 factorial. Well, f double prime just means two derivatives, but no matter how many derivatives you do for e to the x, it's always just going to be e to the x, right? So this is just, again, just going to be e to the 0 divided by 2 factorial. 2 factorial is 1 over 1 times 2, and so that's 1/2. So a2 is 1/2, or I could even just say it's 1 over 2 factorial, right? 2 factorial equals 2. One last term, a3 is going to be the third derivative of f
Yes,
at
sir.
0 divided by 3 factorial. That's f triple prime of 0 divided by 3 factorial. Well, again, triple prime, f of x is just e to the x. So no matter how many derivatives you take, it's still just e to the x. So when you plug in 0, you get e to the 0 over 3 factorial. That's equal to 1 over 3 factorial, or if you want, that's 1 over 6. Right? 3 factorial, right? 3 factorial equals 1 times 2 times 3, that's 6. Okay? And so on. And in general, you get that an is going to be 1 over n factorial. This is the pattern. Right? It's not so hard to see, right? Because if you take n derivatives of f at 0, it's still just e to, maybe I won't do the pattern, I'll actually just write it down. An is equal to the nth derivative of f at 0 over n factorial. But no matter how many derivatives you take, it's still just e to the x. So you get e to the 0 over n factorial, which is equal to 1 over n factorial. Right? So n is 1 over n factorial. And so that means that the series is the sum from n equals 0 to infinity of 1 over n factorial times x to the n, right? This is our an, which we've solved for.
2 hours before it was finished.
Sorry. Deborah? Okay. So this is this an that we've solved for. Or, in other words, if we want to write it out, well, the n equals 0 term, this just gives us 1 plus x to the 1 over 1 factorial, and then plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, and so on. Okay? And it turns out that this function is equal to e to the x. This is the MacLaurin series for e to the x, and this is the MacLaurin series for e to the x. This is the MacLaurin series for e to the x, and this function is actually equal to e to the x. And this is actually true everywhere for all real x. Okay? This is actually equal to e to the x. So you make this MacLaurin series, which is pretty simple because the derivatives of e to the x are so simple to calculate. They're all e to the x. And you get this formula. So 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, gives you e to the x. Okay, so this is pretty amazing, right? You have this exponential function, but actually you can write it as a series. Okay, I'm going to just zoom out just so we can see the whole board again. So any questions on this? Let me just add another page. I'm just going to write down this. So we have that e to the x equals 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. Oh, sorry, not plus 1. It equals x to the 1 plus x squared plus x cubed plus x to the 4th over 4 factorial, so on. What happens if we plug in x equals 1? Well, you get e to the 1, that's just e, and that's equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on. So this actually gives you a formula for e. Right? So formula for e is actually given by taking the sum of this series. right? And what is this actually? That's 1 plus 1 plus 1/2 plus 1/6 plus 1/24, and so on. And it turns out that this is equal to E, which is approximately 2.718. So if you add up all these numbers, you're going to get, it's 1 and then 2 and then 2.5 and 2 2/3 and a little bit more. And it turns out this is going to converge to 2.718. Okay. Okay, so this gives you a series that has a formula for E, because e to the x is equal to this MacLaurin series. Again, I haven't proven that they're equal, but we have shown that the derivatives of this are all the same as the derivatives of this. So that's maybe pretty convincing evidence that they should be equal. And what I want to do is I want to show you a picture of this. I want to show you a picture of this on Desmos. So I'm going to share my my screen. Okay, so let me share Desmos. Okay, so I'm going to write the function. Let me write the function y equals e to the x on my graphing calculator. Y equals e to the x. Okay, so this is the function y equals e to the x. Okay, so now what I'm going to do is I'm going to do certain partial sums of this power series. So I'm going to start with y equals maybe 1 plus x. Well, that's kind of close to e to the x, right? It's a tangent line, but that's kind of actually the best linear approximation to e to the x at 0. So now let me add another term, 1 plus x squared divided by 2, right? That's in green. That seems like it's an even better approximation of e to the x, right? It's getting closer and closer. Let me do one with one more term. So y equals 1 plus x squared divided by 2. And then remember, the next term was plus x cubed divided by, x cubed divided by 6. Now you have this in purple, which looks like it's approximating the red even better, right? I mean, let me zoom in a little bit. If I zoom in, remember e to the x is in red. You can see the colors, what everything is. So e to the x is here in red. The blue is my first approximation. The green is what happens when I add more terms of my series. The purple is what happens when I add even more terms, and I'm going to do one more. Y equals 1 plus x squared divided by 2 plus x cubed divided by 6, and then I'm going to add one more, so this will be in black, plus x to the 4th divided by 24. That's the next term. That's 4 factorial. So this is black. And what you see is that each new one does a better and better job approximating e to the x. You see over here, the black polynomial is almost indistinguishable from the red one. They're equal to like almost exactly the same thing to here. And then it becomes bad as you get far away from 0. But what's going to happen is that as I add more terms, it's going to become a better and better approximation over a bigger and bigger range. Okay, and if I zoom in even one step further, it looks like this black really does look exactly the same as e to the x up until a small amount of the way out. Okay, so the more and more terms I add, maybe I'll if I take away these two just to declutter a little bit, I'll do one more. So y equals 1 plus x squared divided by 2, plus x cubed divided by 6, plus x to the 4th divided by 24, and now I'll do one more term, plus x to the 5th divided by 5 factorial, which is 120. Okay, so this is in kind of orange, and what you see is that the orange is an even better approximation than the black. And somehow, like it approximates it to a further extent here, and then up here it's kind of indistinguishable. Maybe I'll get rid of the purple. So now we really just see 2. I'll zoom in a little bit. You see like already the black and the orange are almost perfect approximations here. And then this one is the actual e to the x. The black is the fourth degree approximation, and this red is the fifth degree approximation. So it does a little bit of a better job before they start moving apart from each other. And so this is the pattern. If you keep adding more and more terms, it's going to start looking more and more like e to the x. And when you take the limit to go out to infinity, it actually is the function e to the x. Okay. All right, so I'm going to stop my share here. Okay, oh good, so we're back to here. Okay, so wait, I just did this. Wait, did I just, oh, I must have this slide twice. Oh, I have this slide twice. Let me eliminate this slide. Okay. All right, so what do I have? Yeah, okay. So turns out you can do this for a lot of other functions. We don't have time to do it, but it turns out that you can do lots and lots of other functions in the same way as e to the x. You can compute a lot of derivatives, and this works. So it turns out that sine of x is equal to x divided by 1 factorial minus x cubed divided by 3 factorial plus x to the fifth divided by 5 factorial minus x to the seventh divided by 7 factorial, and so on. So this works for all real x. There's a similar formula for cosine, but use the even numbers instead of the odd numbers. So 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on. This works for all real x. You can do ln of 1 plus x. It turns out to be x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and so on. This turns out to be valid only for x inside the interval from, so what do I want? For x inside the interval from -1 to 1, the half-open interval here. And then inverse tangent of x is actually equal to x minus x cubed over 3 plus x to the fifth over 5 minus x to the 7 over 7. And this is valid for all x inside the closed interval from -1 to 1. Okay. Okay, so I'm not going to have time to go through all of these examples, but the point is you can do them the same way. You calculate all the coefficients by taking derivatives, evaluating them at 0, and dividing by n factorial. So you get these incredible formulas that all of these functions, these trigonometric and logarithmic and inverse trigonometric, they're all just given by series. And it's all just about figuring out what is the correct coefficients to put in the series. And what's nice about this is that when you're doing calculus, when you want to do derivatives and integrals, every function has its own way of doing it, and it's a lot to remember, and there's lots of rules, and integration is hard, and derivatives have lots of rules, and how do you do trig, and how do you do inverse trig, etc. Whereas series are basically just polynomials. They just go on forever. So if you want to take a derivative of a series, easy. Just take the derivative of every term. They're just polynomials. You want to integrate a series? Easy. Just integrate every term. They're just polynomials. So a lot of times, even though series might seem more complicated, they're actually easier to work with, and they're easier to do calculus with than things like trigonometric functions or logarithmic functions or inverse trig functions. So getting all of these in terms of series actually makes it a little bit more uniform, a little bit easier to operate with them. Okay. Okay, so these are some nice things. And let's just do, examples. So for instance, now we can see let me give these series names. I'll call them 1, 2, 3, and 4. And now we see our first example, right? If you take x equals 1 in series 3, you get that ln of 2 is equal to 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, etc. And if you take x equals 1 in series 4, you get that tangent inverse of 1, which we saw last time is pi over 4. right? Because tangent of pi over 4, that's 45 degrees, is equal to 1. And that's equal to 1 minus 1/3 plus 1/5 minus 1/7, and so on. Okay, so this gives us these series from the beginning. That's how you get these kind of crazy numbers are just equal to series. It all comes from these MacLaurin series, which means it ultimately comes from calculus. It comes from making series whose derivatives give you the right values. And that's how you form these series. Okay, so even a formula like this, which doesn't seem like it has anything to do with calculus, it actually is based on calculus. Okay, and this is a way that you can get the value of pi if you compute enough terms. Okay, any questions on this slide? Okay. Okay, so the last slide of math that we're going to do, before we finish is just 2 reasons why MacLaurin series are useful. So number 2, I guess I talked about already. MacLaurin series can easily be integrated and differentiated, right? So I'm going to give examples for 1 and examples for 2. So maybe I'll start with 1. So MacLaurin series give a good way to approximate f of x when x is close to 0. Okay, so let's look at this. So let's use the series for sine. So sine of x we saw was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So say we want to know what is sine of 0.1. We already talked about other methods of approximating tangent line methods and Newton's method and everything, but this power series gives another way of approximating. And this is actually more what your calculator does. Well, we know that sine of 0.1 radians, that's about 5 or 6 degrees, is equal to 0.1 minus 0.1 cubed over 3 plus 0.1 to the 5th over 5 minus 0.1 to the 7th over 7, etc., right? I'm plugging in 0.1. So let's just take 2 terms so that it's easy, right? Because these terms are getting small very fast, right? You've got, oh, sorry, this is factorials, right? So these terms are getting small very fast, right? So the terms out at the end shouldn't matter that much. So let's see what happens if I just take the first 2 terms. So the first 2 terms, this is 0.1 minus 0.1 cubed is 0.001 divided by 6. Okay, and so what is that? 0.1 minus 0.001 divided by 6. This is equals to 0.0998333, and with 3's, so on. So even, with 2 terms, I can calculate this pretty easily, and I get this value. Now, what's the actual value of sine of 0.1? Let me try to put this in on a calculator. What is sine of 0.1? Turns out it is 0. So actually, sine of 0.1 is 0.099833466, and so on. I mean, the sixes don't repeat, but so look how good an approximation this is. So even just taking 2 terms of this series is already good to 1, 2, 3, 4, 5, 6 decimal places. So using only 2 terms gives the correct value to 6 decimal places. Okay. So that's pretty amazing. We have this series. How would you ever evaluate sine of 0.1 radians otherwise? You'd have to draw a right triangle and measure it carefully. I mean, it's just really hard. You don't have any formulas that are going to give you sine of 0.1 radians. But you do have a series. And maybe it would be hard to evaluate the entire sum of the series, but since most of the terms are very small, you can just take a couple of terms and get a very good approximation. So it turns out that just from using two terms, you get this incredible approximation. You get 6 decimal places. That's as much as you would ever need for any kind of engineering purpose. 6 decimal places is good enough. Okay? So these power series give you really, really good approximations, at least when x is close to 0, when you plug in small values for x. Okay? So that's kind of the first application. What about the second application? Well, the second application is that MacLaurin series are very easy to differentiate and integrate. So let's look at this. If I have e to the x equals 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. So let's say I want to know the derivative of e to the x. Well, we know that it's e to the x, but to do that, we had to do some limits, some complicated procedures. Now, what happens if we just differentiate the series, right? We just do polynomials. That's much easier, right? So if I take the derivative of e to the x, I should just do the derivative one by one. So what do I get? I get 0 plus, well, the derivative of x over 1 factorial is just 1. The derivative of x squared over 2 factorial is 2x over 2 factorial. And then 3x squared over 3 factorial, and then 4x cubed over 4 factorial, and so on. And how does this simplify? Well, this is just, 1 plus, 2x over 2 factorial, 2 over 2, these just cancel out, and you're left with x. 3x squared over 3 factorial, well, remember, how do we cancel out 3 with 3 factorial? Well, 3 factorial is equal to 1 times 2 times 3, so the 3 up here cancels with the 3 down here, and you're left with just 2 factorial. So you get x squared divided by 2 factorial. And now what's next? Well, this 4 factorial over here, this is just 1 times 2 times 3 times 4, right? I'll zoom in a little bit. It's 1 times 2 times 3 times 4. And that means this 4 up here is going to cancel out with a 4, and what you're left with is just 3 factorial. That's what's left in the denominator. So zooming back out again, this is going to be x cubed divided by 3 factorial, and this pattern continues, x to the 4th over 4 factorial, and so on. So we see that if you differentiate this series, what you end up with is exactly the same series again. Right? So this is e to the x, right? Exclamation point, that doesn't mean factorial, that just means it's amazing, right? You take a series and you differentiate it and you get the same series back again. Well, we should expect that, right? Because if you take e to the x and you differentiate, you get e to the x back again. And you can show this by using the series. If you take the series for e to the x and you differentiate, then you get the series for e to the x back again. Okay? But the differentiation with series is much easier. You just do it term by term with polynomials, whereas deriving what that derivative of e to the x is was hard. You had to do some limits and rearrange some stuff and take some limit as h goes to 0 of e to the x minus 1 over e to the h minus 1 over h. There's a lot that went into this. But with series, it just falls out. The derivative of this series is itself because you just do it term by term. Okay? So these are two of the main applications of MacLaurin series. Like, why would you want to replace a function with a series? First, because it lets you approximate values of that function very nicely. And second, because it allows you to do differentiation and integration sometimes much more easily than you can with the original function. Okay? For e to the x, it's okay. It's something we know. But there's lots of series that show up in engineering and differential equations that don't have nice formulas like e to the x. And for these series, the only way to differentiate them or integrate them is by using their series form. Okay, the only way you can do it is by doing it through series. Okay, so any questions here?
Yeah, yeah,
Yep.
done.
Yeah, Prince.
So, yeah, okay. The E derivative of X do not have a constant value when do the solve here. Would A nine have constant value to have a specific value because I'm seeing a exclamation mark here, or is factorial usually?
No. Yeah, this exclamation part, I just mean like to note that it's amazing that if you take the derivative of this series, you just get the same series back. I don't mean factorial.
Okay,
Maybe I don't want to confuse people. I'm going to erase the exclamation mark. Okay. So it's just
okay,
like
okay.
the derivative of e to the x is e to the x, and we see it in the mirror image with its series. We see that the derivative of this series is also itself, right? So it's another way to see that the derivative of e to the x is e to the x without having to calculate limits.
Thank you.
Okay. You're welcome. Um, okay, other questions? Okay, so I think that's where we're going to end the math for this year. So what we've done over the year is we've given what I would say is a highlight of the ideas and main applications of calculus. It was not a comprehensive calculus course. A comprehensive calculus course would have a lot more problems. We'd go a little bit deeper into why these series work. We would do a lot more integration. But it's hard to do a comprehensive course remotely with only 2 hours a week. So what I wanted to do is give you an idea, what is differentiation? What is integration? What does it have to do with physics? What are some things that you can do with it, some applications, and to get an idea of what calculus is about. And also to relate it to the regular high school curriculum through things like sequences and series and limits and things like this and tangent lines. So um, yeah, so I thank you all for sticking with me through this year. I want to just give some acknowledgments to everybody. So first of all, of course, to all of the teachers for, we don't have this without the teachers. So thank you for coming in week after week, after school, after you've worked already, to come and take another class. So thank you for your attention and for a great year. And lots of thanks for everybody who did organization, both for the teacher training program and also for the WITS mathematics competition. So I want to thank Sanjay and Deborah and Charles and Abraham and Alexander. Everybody did organization, either for distributing the data, I mean, especially Deborah for stepping in the middle of the semester when we needed you to make sure that everybody got their data, and to Alexander and Abraham and Charles for helping organize the math competition, and for Sanjay for always, being in touch with me and starting this all off. So thank you all for your incredible organizational efforts. We'd not be able to do this without you. I certainly could not do this program myself. So thank you. So I want to acknowledge and appreciate everybody who's helped make this program work. I want to also thank just organizational, Ministry of Education, the National Science Foundation of the US, who provides all of the funding for the data, my college for supporting me in doing this, so Baruch College of the City University of New York, and of course, I Help Liberia Project for getting me, involved in working with Liberia in the first place. I've been doing it now for 14 years, and it's been really great. So I want to say something about certification because we've been talking about certification on the chat before. So it's the same rules as last year. So certificates will be given to all who participated substantially in the program this year. So if somebody came once to one class, they're not going to get a certificate. So if you attended a significant number of classes, you'll get a certificate of participation. If you attended almost all of the classes, you'll receive a certificate of completion. Certificates of distinction will be given to those who not only attended almost all of the classes, but who also significantly enhanced the class through their active participation and/or effort on the homework problems. And I'll announce the list of people for each certification in the WhatsApp group next week. I'll send it out. I need to go back over the list, the roster of everybody. But in the meantime, make sure that you send your name with the correct spelling to the WhatsApp chat so that we can write it correctly for the certificates. Now, I know there is an issue that last year's people still have not received last year's certificates. I know I have signed the certificates. There is a space on the certificates for a signature from the ministry, I think. Let me make sure which space I have actually. Let me go try and find my computer files of the certificates. So my computer files of the certificates for last year. Where's my certificates from last year? Here they are. So certificates from last year, they're supposed to be signed by me and by Nathaniel Sisko, who's the Assistant Minister for Science, Technology, Vocational, and Special and Inclusive Education at the ministry. So there's a space for Nathaniel to sign. I don't know if he is signing or if there's going to be a ceremony or what. Unfortunately, after I've been told who's supposed to sign, I type that into the certificate with a space for them, and I sent them to Liberia, and I don't know the progress of getting them signed by this minister. I don't know if Deborah or anybody else can shed some light. But the certificates are in Liberia, and I have signed them, and I hope that they can be gotten to you as soon as possible. But unfortunately, once they're in Liberia, I can't really help with the distribution. So I hope it will happen quickly, and we can continue this on the WhatsApp to figure out what's going to go on. The new certificates I'm going to make in the next week or two, and I'm going to find somebody traveling to Liberia to bring them over. So they will arrive in Liberia sometime this summer, and hopefully they'll get distributed faster than last year's were. I'm very sorry. Apologize greatly that people have not received their certificates from last year yet. Yes, Deborah, do you want to speak? Please do.
Good evening, everybody. Thank you, Dada Opos. Thank you for everything you do for Liberia. Um, Concerning the certificates, Mr. Buble is in charge of the certificate, and I will try to get to him next week, Monday, and see how best we can distribute the certificates and have a common program, because that was what he was actually expecting to do, to have a common program with the minister of the STEM division and the director as well, Masangi. So I will make some inquiry on Monday at the office when I go there, and then we'll see how best we can distribute it this new month that is coming. Yeah, but actually, I saw the certificates; they are already signed, everything. So it was Mr. Booker who was really in charge of it. But I will try to make a follow up that everybody received the certificates next month.
Okay, great. So they're already signed by the minister also?
Yes,
Oh,
it is
great.
signed
Okay.
already.
Okay, wonderful. Okay, great. So, okay, at least they're all signed. They're all there. That's great. Okay, so I mentioned this briefly, but I want to say something also about next year. So next year is the final year of the teacher training program. We have funding for 5 years, and it will run differently than the previous years. The focus is going to be on making the teacher training sustainable when I'm no longer running it. So the idea is to make the program a sustainable program that can run perpetually by Liberians in Liberia. So I don't yet know exactly how this will work. It's one of the things that I'm going to be thinking about in the summer. I'm going to be talking to Mr. Randolph. I'm going to be talking to the iHelp team. We're going to be brainstorming ideas about what's exactly the right way to run next year. But, for the last 4 years, it's all been we pick some math and we learn about some math. And that's not going to be how it is. It's going to be, more interactive, more leadership from the Liberian team. And I'm very open to suggestions on the chat of ideas about how to get this to work. And I'm going to be spending the summer talking to Mr. Randolph, talking to AB, talking to Deborah and Sange and Brople and everybody about, what's the best way to do this, because I don't want I don't want everything to just end once there's no more data funding after next year. I want to figure out some way that this can have a lasting impact. Okay, so that's my project for the summer, is to try to figure out what's the right way to do that. And then when we restart in September, things will look a little bit different, but I think they should remain interesting and productive and will be helpful for the long run. Okay, so that's the plan for next year. Plan is kind of, there is no plan, but it's going to be different, and I'm going to figure out a plan at some point during the summer. Okay. So that is the idea for next year. It may mean that we don't meet as often, that we meet in smaller groups, but each small group doesn't meet quite as often. I meet with different small groups at different times. It's a possibility. All sorts of ideas. We'll think about a lot of ideas, and then we'll figure out what's the right way to proceed. So that's next year. And just one more time to everybody to thank you for all your participation and attention this year. Okay, so the question, James says, will there be recruitment for next year's classes? I think we could possibly recruit some. We have to talk about that. It may only make sense to have teachers that have already participated so that they, are familiar with what we've been doing. Or it may make sense to recruit new teachers. So I don't want to make a commitment yet before I have a better idea of what the program will look like. So I'm sorry, I can't give a definitive answer. There might be recruitment or there might not. It depends on what the program will look like. So I have to spend time this summer thinking about that. Okay. So thank you once again to everybody, and it's been an honor to work with you all and to witness your dedication and persistence, and I've also had a lot of fun. So this has been great. So thank you.
Thank you very much. Thank you to the team.
Yes. Thank you to Harrison. Oh, let me just stop the recording.